Unit 4 Correction Analysis. Unit 4 Correlation Analysis. Hello learners, let us get started with Unit 4 from the course Statistical Quantitative Techniques. The name of the unit is Correlation Analysis. Let us begin the session. Correlation and Causality. Correlation and Causality. The conventional dictum, correlation does not imply causation. Correlation does not imply causation means that correlation cannot be validly used to infer a causal relationship between the variables. This dictum should not be taken to mean that correlation cannot indicate causal relations. However, the causes underlying the correlation, if any, may be indirect and unknown. Consequently, establishing a correlation between two variables is not enough condition to establish a causal relation in either direction. For example, hot wave may cause both reduction in purchase of warm clothing and increase in ice cream purchase, which may mean that warm clothing purchase are correlated with ice cream purchase. However, a reduction in warm clothing purchase does not cause ice cream purchase, and ice cream purchase does not cause a reduction in warm cloth purchase. A correlation between age and height in children is causally transparent, but a correlation between the mood and health of the people is less so. Does improved mood lead to improved health? Does good health lead to good mood? Or does some other factor underlie both? Or is it pure coincidence? In other words, a correlation can be taken as evidence for a possible causal relation, but not indicative what causal relation, if any, might be. Correlation and linearity. While Pearson correlation indicates the strength of a linear relationship between two variables, its value alone may not be enough to evaluate this relationship, especially in the case where assumptions of normality is incorrect. Sum of the squares. We introduced a notation earlier in the course called sum of squares. This notation was the SS notation and will make these formulas much easier to work with. Now let us understand Pearson correlation coefficient. There is a measure of linear correlation. The population parameter is denoted by Greek letter rho, and the sample statistics is denoted by the Roman letter R. Here some properties of R. R is the only measure of the strength of linear relationship. There are other kinds of relationship beside this linear. R is always between -1 and +1 inclusive. -1 refers to negative linear correlation, +1 refers to or predict positive linear correlation. Or always between -1 and +1 inclusive of 0. -1 means perfect negative linear correlation and +1 means perfect positive linear correlation. R has the sum sign as the slope of the regression, best fit line. R does not change if the independent x and independent y variable are interchanged. R does not change if the scale on either variable is changed. You may multiply, divide, add, subtract a value 2 from all the x values or y values without changing the values of R. R has a student's distribution. Here formula for R, don't worry about it, we will not be finding it in this way. This formula can be simplified through some simple algebra and then some substitution using SS notation discussed earlier. If you divide numerator and denominator by n, then you will get the same thing, which is starting to hopefully look familiar. For example, 4 plus 4 by 2 is 2. Similarly, 4 into 2, 8. 2 multiply 2, 4. Again 8 by 4 is 2. So, when you divide a numerator and denominator by n, then the value you get something which is starting to hopefully look familiar. Each of these values have been seen before in the sum of the squares notation section. So, the linear correlation coefficient can be written in terms of sum of squares. Remember that hypothesis testing is always done under the assumptions that null hypothesis is true. Now let's talk about Spearman's rank correlation coefficient. In statistics, Spearman rank correlation coefficient or Spearman's rho, named after Charles Spearman, often denoted by the Greek letter rho, or as RS, is a non-parametric measure of correlation. That is, it assesses how well an arbitrary monotonic function could describe the relation between two variables without making any other assumptions about the particular nature of relationship between the variables. Certain other measures of correlation are parametric in the sense of being based on possible relationship of a parameterized form, such as a linear relationship. In principle, rho is simply a special case of the Pearson product moment coefficient, in which two sets of data xi and yi are converted to rankings small xi and small yi before calculating the coefficient. In practice, however, a simple procedure is normally used to calculate rho. The rho scores are converted to ranks, and the difference di between the ranks of each observation on the two variables are calculated. These sort of studies involve comparing two variables, for example, income and crime, smoking habit and health, in order to see if there might be some connection and perhaps even a suggestion of cause. As a cigarette smoking habit rises, do health problem also rise? As income decreases, does the frequency of crime increases? As people grow old, do they have become less or more tolerant of others? Correlation is an extremely important analytical tool which enables us to begin to sort out claims about important connections which may or may not be true. Amount of smoking and incidence of lung cancer, HIV infection and the onset of AIDS, the age of car and its value, television programming of playoff games and attendance at lectures, poverty and crime, IQ tests and income levels, intelligence and heredity, age and mechanical skills, and so on. People make claim about such matters all the time. The principle of correlation enables us to investigate such claims in order to understand whether they are true or not, and if true, just what the strength of the relationship might be. Finally, we come to an end of this session. Thanks for watching this video.